Hey everyone, welcome to this extra video about the one-dimensional splitting for worked example number 4. I wanted to talk in more detail about the splitting that we see for this example, but I didn't think that it necessarily needed to be included with the whole worked example itself. So that said, there are a few spoilers in here. If you haven't watched the worked example video all the way through to the end, I recommend that you do that first so that you understand how I made the base level assignments. And then you can come to this video to get a little bit more behind the scenes about how we can bolster those assignments by looking at the splitting using different J values and thinking about a little bit of the arrangement of these protons in space. So to start, let's look at B through F because those ones have fairly clear splitting, at least to some degree, and then we can maybe make some annotations on that splitting. I would say for G through I, those signals are they're too messy, and without the ability to zoom in and get a higher resolution, I don't think we'll really be able to tell much about the splitting from those, so we'll just leave those B for now. Back to proton B. We labeled that as a doublet of doublets, and now we have to ask ourselves, does that splitting still make sense for the position we put hydrogen B? If you feel like you maybe need a little bit of a refresher to tackle this question about a doublet of doublets and whether or not that backs up our assignment, I would recommend strongly that you go back to our NMR unit from last semester to refresh yourself on why a doublet of doublets might occur. I'll talk briefly about it, but to understand why that arises, you should definitely go back and just give a quick look at your notes to remind yourself where this comes from. So B should be split by F because those are totally dissimilar neighbors, and there is one proton F, so that would give us a doublet. That part adds up. And we have to think about where that other doublet comes from. It has to come from some other dissimilar chemical neighbor. If you're looking around to say what other protons are adjacent to B, you could look at this amine hydrogen, but those almost never show any splitting to carbon-based hydrogens that are adjacent. Same thing with, say, an OH proton. We don't see those participating in splitting in our one-dimensional proton NMR, so it can't be that one. The only other proton that's at all adjacent to B is proton C, but they're on the same carbon, so can they split each other? Yes, they can. And the reason that that is has to do with the stereochemistry of our molecule. One thing that's really important to keep in mind with this structure, and definitely for the structure in your post lab, is that we haven't really talked about stereochemistry yet and how that can affect NMR. If I bring in another copy of our structure just so that we can keep our annotations at the top, we can look a little bit more clearly at the stereochemistry in this molecule. And you may be looking at it and saying, Grace, I don't see any stereochemistry. Well, we have to think very carefully about this position here. That hydrogen that I've just filled in, we think is hydrogen F. And because of the hydrogen there, this CH2 that's close to other CH2 groups, this CH2 that's adjacent to the amine, and the ethyl ester here, that carbon that I will label with a red star here is a chiral center. So there's a couple of different ways we could represent that on this drawing. One of those would be to give a wedge here to the ester to show that it is coming out of the plane of the page at us. Or similarly, we could cover up this full bond with a dash to say, no, it's going back behind us. Those are a pair of enantiomers that could both be represented by the structure that we have up here at the top. Because our original structure only gives us a single bond, solid bond, no stereochemical information, we can't be certain if we have one or the other stereoisomer. In fact, we might have both. That could explain why we see such strange splitting here. Either way, we do have to be thinking about the stereochemical nature of this compound as we move forward with our analysis. What matters more to us than whether we have R or S or a racemic mixture of the two is how that stereocenter on our molecule will have an effect on the other protons that are nearby. It turns out that the stereocenter at that position will have an effect not only on hydrogen C, which is the one we were just taking a look at, but it will also have an effect on the majority of the hydrogens that we see in this molecule. So, at first glance, hydrogens B and C are attached to the same carbon, they're right next to the same functional groups, So they would seemingly have the exact same chemical shift and be perfectly equivalent. Because of their adjacency to that chiral center, and also helped by the fact that they're kind of partially locked in this ring, they are actually very different from one another. This has to do with that stereocenter itself. Regardless of R or S, that stereocenter is locked in place. That means that proton F and our ethyl ester are relatively fixed in space compared to, say, a straight chain alkane, right? The straight chain alkane has a lot more flexibility and it doesn't have any chiral centers. Proton F and our ethyl ester are relatively fixed in space. When we consider how they're arranged in space, that makes the arrangement of B and C in space come into question as well. Let's remove our stereocenters and think about something else that I'm sure everyone is really happy to see come back, the chair. If I arbitrarily pick one of our isomers of this compound, I'm going to just pick the one where HF is sticking up axial and our ethyl ester is pointing down equatorial, and then fill in H, B, and C again randomly, just to illustrate the point that if HF is in this position, it would be relatively locked. Even though there's some flexibility of the chair, we want to keep this larger ethyl ester group in the equatorial position. That means that HC is stuck in a fairly different arrangement around the ring than, say, HB would be. HC is at a very different angle to HF than HB is. So here we're talking about the dihedral angle and our Karplus curve. We'll come back to that more in a moment. So the arrangement of HB and HC to one another and their relationship to that stereocenter means that their chemical environments are not actually the same. So if we were to be circling these chemical environments with different colors, we would say that HB is in a distinctly different chemical environment than HC is, based on their angle and relationship in space to that chiral center. The other way to look at this is to play the substitution game, which you may have learned last fall. If we were to substitute B or C with some other, heteroatom, something that would be distinctly different in our Kahn-Ingold-Prelog rules, we want to see if that substitution would create a new stereocenter. In this case, it absolutely would. And because of our existing stereocenter at that red starred carbon, not only would it make a new stereocenter, it would create a pair of diastereomers. Thus, the term that we use for protons B and C and many of the other protons in this molecule is diastereotopic. We take this to mean if you were to substitute one and the other protons for some other atom or molecule of interest, that you would create a new pair of diastereomers. What this means for NMR is that because they are non-interchangeable, they are not equivalent, they split one another, even though otherwise on the structure, they would seem to be quite similar. So not only do we see the coupling of F to B that we talked about earlier, but we also see the coupling of B to C as well. That explains why we get our doublet of doublets. Then if we had a little bit more information about which isomer this was and a little bit more fine detail about the Hertz values of the splitting here, we can make an even more accurate assignment of which proton is B and which proton is C. Let's do a little thought experiment about the splitting using this chair that I have down here. Again, I don't know if it's the right one for this data or not, but working through this splitting practice, thinking about the magnitudes of different J's will be really, really useful to you on your post-lab assignment. So if we're looking at HB, we're saying HB is split by HF like so, and the magnitude of the splitting is going to have to do a bit with the dihedral angle between the two. So go ahead and draw a chair Newman of this if you have the spare time to see that the angle between HF and HB is somewhere on the order of 60 degrees. Now you can take that angle and look at your Karplus curve to see the approximate magnitude of how many hertz HF would split HB by. We also know that HB is going to be split by HC, and the angle there between the two of them is about 109.5, right, for the typical geometry of an sp3 hybridized carbon. There's going to be a very large splitting of B on C because they are geminal protons, which means attached to the same carbon. So the splitting for this is somewhere on the order of 12 to 15 hertz. You may want to refresh yourself on these values on your common J coupling sheet. So regardless of what the actual numbers are, we can think about what that might look like on our structure. So looking at the signal for B, we know we have kind of the larger doublet that's centered around here and here. That part is going to be split by our biggest J. In this case, I'm fairly certain that that's going to be the geminal splitting of B to C. Then additionally, we have this very fine degree splitting that you can just barely see in the tops of those peaks. The J value there that resolves those peaks is very small. You can tell because they're basically not very well resolved. They don't split up hardly at all. You can just see a little kind of fork in the top of the peak. So the J coupling for that is going to be pretty small, and that corresponds to the smaller dihedral angle of this other HF to HB coupling. So even if you don't have the exact numbers to hand, while you're working on these problems, particularly the post lab, you want to be thinking about different J values. You can ask yourself, do I have a big J? Do I have a small J? Perhaps all of my J's are equal? These might help give you some insight, whether from the forward direction where you say, I'm looking at peak B and I see that I have what looks like a doublet, but with some complex splitting, could be a doublet of doublets. That might mean big J, small j. Then you would want to try to find a position for proton B that would have such an arrangement of a big J value from either a large dihedral angle or a geminal coupling, and then a small j from a smaller angle. Or it can come from the sort of backwards direction. We might say, I'm looking at this position here, and I think that could be B. Do my neighbors make sense that one would give me a large J and one would give me a small j? And then you can check with your peak shape to confirm or deny that that is the case. So as I've said before, there's a lot of different ways to approach these types of problems. Regardless of what method you take or what order you want to analyze your data in, you definitely want to make sure that you're thinking about things like J values and splitting to help you make the best possible assignments. So I think we've pretty much covered the waterfront for peak B in terms of its splitting and its neighbors. So let's move on and at least talk about C, D, and E. Those remaining three have fairly well resolved splitting, at least better than the rest. I think we'll save F through I and just say that their splitting is pretty complex. We could parse through it a little bit more if we wanted to, but even if we came up with assignments of what we would expect to see from them, you'd end up with a really complex peak shape that's probably more in depth than we need to go. If you want to, feel free, but let's focus on some of the slightly more simplistic ones just to keep in our practice. Plus, you're not going to be expected to come up with any super complex splitting patterns for your post lab. They'd be more something on the order of what we've already seen for B, doublet of doublets, doublet of triplets, that kind of thing. So let's move on to peak C. If you hopefully watched the example video already, you'll know why these assignments down here have just changed. But let's see if we can make sense of the splitting at C. So now C is over here on this carbon. And let's think about what we would expect to see for its neighbors. We would expect, without looking at our 1D data, that C is split by E to some extent, so that's a doublet. C being split by I would be a doublet of doublets, and C being split by H would be another doublet, so we would expect a doublet of doublets splitting here. We don't exactly see that in our one-dimensional data when we go to look at it. What it looks more like to me would be a doublet of triplets. So what I think is happening here is that HC is split by HE to some big J that we can see in the center of our lines there. So that is splitting it into a large doublet. And then H prime and I will be splitting HC to some extent where they are actually looking pretty similar so that it looks like we have E as one neighbor and H prime and I as two neighbors that are quite similar. So that's where I think we're seeing those two kind of splitting together to give a triplet. So we'll label that splitting as kind of a triplet for a smaller J. And as I mentioned before, the geminal splitting of C by E would be the doublet for a larger J. So we would call this a doublet of triplets. You always read the big J and then the small j. And I think if you use a little bit of imagination, you can see that peak shape here, that it looks like a couple of messy triplets that are kind of smushed close together to form a doublet. So a doublet of triplets. Let's take a look at D. So when we talked about B and C in our original analysis, when we kind of put them together on the same carbon, I was saying that we would expect the other hydrogen there, which turns out to be proton D, to look like it has a fairly similar splitting pattern to B. Now that's sort of true, but it's not exactly true. Let's get into it. If we're focusing on D, we know that D should be split by B for a big J, geminal coupling, and we would expect HD to also be split by F to some kind of a J. We don't exactly know what the magnitude of that J would be. It's also always based on the angle. So we would expect to see D as a doublet of doublets. But we labeled it earlier as a triplet because it does kind of look like a triplet, right? So what's going on there? The thing that's pretty hard to see on this, would be better if we could zoom in, is right here in the middle of that kind of triplet looking peak shape. It looks like we have some fine splitting, but if I remove the circle, it doesn't look like we have fine splitting really on either of the exterior peaks. So what is that about? What that is about is our doublet of doublets just having kind of a weird overlap. So how can we explain this? I'm going to use the lower diagram and just change out our labels here a little bit. We'll trade HC for HD because we know that that's actually the partner that should be there. So using our J values from earlier, we said that yes, our geminal coupling is going to be on the order of 12 to 15 hertz. That's a pretty big coupling. And then if we think about F to D now, those are 180 degrees apart. That's also going to be a really big J, somewhere on the order of 14 to 16 hertz. So because we have not just one big J, but two big Js, what happens is that the resolution of our doublet of doublets changes. So I'm going to draw kind of a cartoon that looks more like what we have at B, where we have a big J that I'll highlight here in purple, and then we have a little j here in orange. When we have two big J's, what happens is that we have kind of a doublet of doublets that are pretty big, like this, where the big J is going to be very similar to the slightly smaller J. So this cartoon doesn't really do it justice, but the case that we're seeing here is that the doublet of doublets has overlapped in such a way that this central peak is moving in that way, and also this one is moving in that way. Or you can think about them as kind of overlapping one another. Hey everyone, to show what I'm trying to explain here, I figured turn the camera on for a second because it's kind of hard to show on the iPad. So what you'll need is two hands to make two peace signs to sort of represent a doublet of doublets. And then you can sort of move them around like what I'm trying to show you on this cartoon. If we take our doublet of doublets like so, and we move them closer and closer together based on the J splittings, what happens is at some point it stops looking so much like two doublets and it starts to coalesce together to form what looks more like a triplet or kind of a W shape. And then if you keep going, what happens is you start to see these two peaks emerge again. And that's where we get that fine splitting of that central portion of the peak. So hopefully this gives you a little bit better of an idea than that bad cartoon I just drew did. So the end result is that you get something that is truly a doublet of doublets that's just overlapping. So it'll look a little bit more like this and can fool you into thinking it's a triplet, but it's still a doublet of doublets. So I know that that may not be easy to see just off the top of your head without really diving in deep, but that's the point of these exercises, is to practice these deep dives. You'll have to do a little bit of this analysis for your post lab, maybe not quite to the extent that we're practicing it here, but that's why it's a really good warm up so that you're ready for that post lab assignment. So now that we've made these clarifications, let's go in and actually change our annotations a little bit here. We said that C looks more like a doublet of triplets, and D is truly a doublet of doublets, even if it doesn't look so much like it. That's the splitting that we would expect to see based on where it's positioned, and we can explain it using our overlapping doublet of doublets method. And now let's wrap up by talking about E. We initially assigned this one to be a triplet But again, we put a little asterisk there to say, yeah, there's some fine splitting going on that we're not 100% certain about. So let's go back and see if it seems to hold up now. Looking at the position HE is in, it's sort of a similar situation to HC. We would expect a big J geminal splitting here of HE by HC, and we would also expect H prime and I to split it as well to some other J, we're not exactly sure which. So when we were looking at C, it seemed like they kind of combined together to be very similar splittings. And so we kind of arrived at H prime and I appearing to hydrogen C as though they were fairly similar. And we got out of that a doublet of triplets. So looking at E doesn't look like a doublet of triplets to me. I think there's something else happening here that might be worth going back to our chair for. So let's remove some of these annotations so that we can think clearly about the other side of the molecule. Since we're not focusing on H prime or I, I'm just going to arbitrarily fill those in at either position. It doesn't really matter which, because I said we're not focusing on them. But I do want to assign HC and HE very specific positions that I think will help back up this splitting pattern. So we said that HC seemed to have H prime and I be really similar to it. And I think the way that we could achieve that is if we put HC here in the equatorial up position. If we think about it in terms of a Newman projection, it works out pretty nicely because HC will have a gauche or 60-degree interaction with both HI and HH. If you don't believe me, you can draw a quick chair Newman or even just a single Newman might help you visualize this. If we then put HE in the down axial position, that's going to give us a different story than what we just saw for HC. So let's remove these HC annotations and think about HE. So we agreed that we had our geminal coupling here for about 12 to 15 hertz. And then we have two other couplings to attend to. We have HI to HE, which is another gauche interaction that's 60 degrees. So that'll be a fairly small J. But now H prime to E is a 180-degree angle. And that's going to have another really big J, so somewhere 14 to 16 hertz. Now, if we think about how this would play out in the 1D NMR, we have two J splittings that are quite large, right? So if we think about those together, that's like having two neighbors that are splitting you to the same extent, even though they're not exactly identical neighbors. So you could think about that as kind of forming almost a triplet, right? So two neighbors splitting to a large degree would give you a triplet. Then we still have this remaining smaller J splitting that would take the triplet of large splitting and split each of those into a doublet. That is what I think we are seeing up here at E. So it's hard to see on the central peak, but I think on either side here or here, you can see a little bit of fine splitting to it. And I think that is happening in the central peak as well. It makes it look to me like it's presenting as a triplet of doublets. So again, big J first, triplet, and then doublets is the small j, a triplet of doublets. So there's a little bit more practice on looking at fine detail splitting in the one-dimensional NMR. The pieces that you have for your post-lab altogether, both of the 1D spectra and both of the 2D spectra, should be plenty enough for you to dive in and get a really good first guess before you need to do fine detail splitting. But when you do, hopefully this was a good refresher for that. But when you do, I hope this refresher came in handy. If you have any questions about this example or your post lab, feel free to leave it in the comments or come to my office hours. Thanks for watching.